Here we go. So, ladies and gentlemen, welcome. Today we are talking about regarding statistics and data analysis. We are looking at measures of variability. So previously, we looked at measures of central tendency, where we summarized a list of numbers with a single number that kind of represented the middle number-ish, right? Well, a number that represented the center of the data. Though that concept is considered an average. All right, so today we're talking about variability. So not a number that represents the middleness of that list, but a number that represents the dispersity of that list.
Big word.
All right, like how densely populated your data is about the middle, perhaps. So the first measure of variability that we've heard of is probably the range. And I think I've defined this before. It's the highest number minus the lowest number, right?
Yeah, you described that yesterday.
Yeah, I think we have.
No, we didn't.
Okay.
Yeah, we definitely did.
So the range is a type of variability. All right?
Oh, you're right, we did.
So, for instance, let's consider two sets of data. What if I've got two, let's say 3, 5, 7
So 7 minus 2.
is my first set of data,
7 minus 2.
right? And let's say that my next set of data is 0, 0, and 1, and let's see, and I'll do 7, I think. And I think I broke my plan, but that's okay. And let's say I have, let's see, what did I do?
All right.
I think I want this to be 8.
Make it to 8 without erasing it.
Like that?
Yeah.
Sure. 8, and we'll do, well, maybe I do want a 7 in there. Well. YOLO, you only live once, that's right. So, looking at these two lists, what is the mean of this list? What is my X bar?
2, 3.
17 divided by 2?
4.
Is it what? Wait.
4.
Divided by 4. Okay. So it's like 4 1/4, I think. And what is X bar over here?
1, 2, 3, 4, 5, 6.
So I could add them all up, divide by 6, right? I think it ends up being 4. Could someone verify? Let's see.
Kim.
8 plus 8 plus 8. Yeah. So I think it works out, right? So even though both of these have means that are similar, their ranges are different, right? 23, did I add wrong? Yeah, don't forget the 1. 1 and 7 is 8, and then 3 8s is 24. Divided by 6 is 4. Yeah. So what is the range here? That would be 7 minus 2, which is 5.
8
Where the range
0,
here is 8 minus 0,
which is 8.
which is 8. All right, so these two sets of data, even though they have similar averages, their dispersity is different, right? This one's spread out more, where this one's kind of more densely clustered, right? So that's kind of be the idea of variability, is kind of how spread out our data is. And eventually we'll talk about how spread out it is about the mean. So like how close are our numbers around the middle. So measures of variability, range is the first one we've seen before. Now a visual representation of variability is a box and whisker. plot, whisker plot. Have you guys heard of a box and whisker plot? I'll show you what a box and whisker plot looks like.
Is it a box with whiskers on it?
Yes, you got it. So suppose I have got like a number line or something. I'm not even going to label this. All right. And above this, I'm going to draw a box and some whiskers. All right. So the first number I'm going to represent is the median. And I represent it kind of with this vertical line. Then I might have another number, which we'll call Q1.
Q1.
And another number called Q3.
What happened to Q2?
Turns out Q2 is synonymous with the median.
Okay, now where are the whiskers?
So here's our box, and then our whiskers, I could have something like this. There's a whisker, and this would be the highest point, right? High. And then I could have something like this as another whisker, and this would be the low point. Okay?
They look kind of like more like arms.
Yeah, a little bit. And then sometimes it's possible to have like another data point where maybe this isn't technically the highest point, and there's the concept of an outlier. I'll define an outlier for us as well. So the median, what's the median again for a set of data? What's it mean? What's a median mean?
And whiskers.
The middle number, right? So it turns out the median, also known as quartile 2, all right, that's what the Q's are for quartile, is the middle number of the data. All right? It turns out that quartile 1, well, I'll define it in a moment, is the middle of the first half of data. Okay? The median, which is also quartile 2, is the middle of the whole set. And quartile 3, what do you think quartile 3 is? Yes, the middle of the second half.
Q1 is the middle.
And the halves are defined by quartile 2. All right, so what we'll end up doing is we'll find out what quartile 2 is, and we'll remove that from the data, and then we'll take the first half of data and find another median, and take the second half of the data and find the other median. So the reason these are called quartiles is it breaks your data up into quarters, right? Quartile, quarts, 4 quarts in a gallon, quarter, 4 quarters in a dollar, right? Quartile. So what this means is that in each of these ranges, you have 25% of your data represented.
That looks like it may be more like 50 though.
Well, that's why this is a visual representation of the dispersity of the data. It turns out this is the smallest 25% range right here, right? This fourth region here. What this means is 25% of the data occurs in this short little gap. So the data is very dense here, all right? So like if I had data points, they would all be really dense. This one is the largest region, so these data points would be kind of fewer and farther between. Still the same number of data points, it just they happen to fill a larger space. And then these ones are about the same, right? So it has to do with the dispersity of the data. So I've got a high concentration of data occurring between those values, right? So if I was talking about like student grades and I had a lot of student grades between 80 and 85 or something like that, compared to like 80 to maybe this is all the way down to like 65 or something like that. So like I've got a large concentration here, and then the next 25% is spread out throughout the data. Okay, so it kind of visually clusters the information for us. Also, what I could say is half of my data is greater than 65 in this case, or something like that. I don't think the scale actually even works out. I didn't count it or anything, but you get the idea. Yeah, because that'd be 75, 70. Yeah, doesn't work out. Not to scale. But yeah, so it's a visual representation of the density of our data. Okay? And then you could say all sorts of things like 75% of your data is beyond quartile 1 or whatever it is. And then you could kind of even use that as like some probabilities if you wanted to figure out at random what's the likelihood that I select a student that has a grade between 80 and 85. You have a 25% chance of doing that, right? Something like that.
That's very low. And what's a outlier? Is it something that lies to the box because it's not connected to the box at all?
Well, outliers would be if... Now the concept, let me describe it in general. The concept of an outlier is this. If I have a student that is so far advanced beyond anyone else, all right, where they don't even fit in the rest of the group, all right, that's an outlier. Like, you should probably be in 17th grade or whatever it is. What?
It's like the one erratic number.
Okay, yep. I know what you're saying now. Right. In terms of like a scientific experiment, right, if I was like calculating like temperatures of, humans or whatever and like, 98.6 or whatever, all that, and then I end up having like one person that's like 104, like you'd be like there's something wrong with that person, like, all right, their temperature's not right. They should probably go see a doctor. Like something's wrong. Or on the other end, you could also have outliers like way down here, where it's just like so far below something like outliers. We'll actually pretty much exclude them from our data because we're like something's off here. Maybe the tool I was measuring with was off. Maybe I left the thermometer on a light bulb. Like something's off, right? So we'll often exclude outliers from our data because they'll skew our numbers. They'll kind of mess things up where likely there's some explanation as to why it didn't fit. So let's see. There's a couple little formulas. Let's see. The interquartile range.
The
So the interquartile range is the difference between Q1 and Q3, or Q3 minus Q1.
Isn't your quartile one word?
I think it's hyphenated. Yeah, it's hyphenated.
Where?
Yeah, the E's are like evolving into cursive L's here. And then there's the concept of the semi-interquartile range. Actually, no, you're right. Interquartile is one word. Semi-interquartile is hyphenated. Classic.
Classic Mr. Warning.
Yeah. I don't get paid to teach how to word language letters.
English?
Yep. Let's see. So here we are. So I can undo that hyphen. And then we bring those closer together. And I'd lowercase that q. I'll do that. Watch this. This is going to be an awesome lowercase q. It's going to be like the king q.
That's pretty bad. I'm pretty sure you're supposed to... Q is...
Wouldn't it be the plain key?
Bam.
I'm
You
sure
got it.
Q's like that.
So
Cursive
the
Q.
semi-interquartile range is Q3 minus Q1 all divided by 2. And this one actually is also abbreviated by Q sub R is how you can refer to the semi-interquartile range. And so you could say that the semi-interquartile range is kind of the average
You've got the line.
difference between your middle two quartiles. All right. There it is. Good call, good call. So the semi-interquartile range here, I would take Q3 and subtract Q1, right? And then the semi-interquartile range would give me kind of the average distance between those. So the semi-QR would kind of be whatever the average was, right? The midpoint between Q3 and Q1. All right, so we don't actually use that often other than the fact that it's used in the definition of an outlier, which is crazy. So let's see. Let me write this down for outliers. So outliers, okay, are extreme values that are more than 1.5 times the interquartile range. So not QR, unfortunately. No, sadly it doesn't. I guess you could call it QR times 2. Because it would just double that and then cancel it out, if you really wanted to. So 1.5 times the interquartile range beyond the upper and lower quartiles. Man, such a crazy definition.
Crazy, man.
All right, but the concept of an outlier is what I really care about you understanding. It's just like it's so far beyond that there was probably some error in the data that was read. So if this is my interquartile range, all right, I would take this quartile, right, and then do 1.5 times that, right? So if it would have to be like that and a little bit more. And this data would still have to be past that. Okay, so so if this was like 1, let's see, I'll just call it 2QR, and then this is another half of that. The outlier would have to be beyond that much more. So it's kind of a weird definition, but that's the idea behind it, is that it's beyond the data in either direction, high or low, that it skews our numbers, so we ignore it, essentially. Okay, so that is a visual representation of variability within a data set. And now I want to talk about mean deviation. And we're going to figure this out. We're going to program this in Excel as well. So mean deviation.
I'm not supposed to wait for this hell.
Yeah, we'll be allowed to use that. Oh no, what did I do? Uh-oh. That's no good. And we'll pretend that's fixed. Nope. Oh dear. Uh-oh. Watch this. Here we go. All right, full screen. Nope. This is busted. What did I do wrong, guys? Well, I'm just going to roll with it. Mean. All right. Wow, that's bad. Catastrophic failure with my window size. All right, here we go. All right. Problem solved. No one saw anything. All right, where's the edge of my screen? Mean deviation.
You're all screwed up.
Yeah, there's everything's going.
That's all right. It's going to be fine, everybody. It's going to be fine. All right, so mean deviation. So we understand what the concept of a mean is. That's the average, right? The primary measure of central tendency. Deviation, what does the word deviation mean, do you think?
It's like something that goes off the norm.
Yeah, something, yeah, exactly, right? How it deviates from the norm, something that goes off the norm. So mean deviation, in this case, is going to be described as the average distance that any point is from the mean. So that's what mean deviation means. So let's write that down. So it is the average distance that the data is from the mean. And this is going to measure our variability. So I'll know where the middle is, right? And I'll basically find all of those distances that my data is from the mean, and then figure out what's the average distance. And if that average distance is large, then that means my data is very dispersed. If the average distance from the mean is small, then that means like not only is that the middle number, but all of my data is really close to that middle number, right? It's all tightly clumped together. So let's look at what the formula for mean deviation is. So mean deviation is equal to 1 over n multiplied by. So I'm dividing it by how many things I have, n values, multiplied by the sum of I equals 1 to n of the absolute value of xi minus x bar. And I guess I'll define what some of these values are. So n is the number of values. Xi is a piece of data. And x bar is the mean. Right? So let's look at what this formula tells us to do. It says subtract the mean from your
Is it the
point.
absolute value?
That is absolute value symbols, yep. So it subtracts, it finds the difference between all of your data and the mean. It takes the absolute value of those distances, all right, adds them all together and divides by how many there are. So that's giving us, once again, the average distance that our data is from the mean. So let's open up Excel. And let me get some data here. What's some good data today? What should I collect for data?
8, 4,
Okay.
90,
90. Okay.
9,
9,
4, 0.
4, 0. That would be an outlier at this point. 12.
15.
15.
55,
55.
6.
6.
28,
28.
15. Oh, 15's already up there. Oh, well.
Well, it's all right. We can have a data point show up multiple times.
11.
Yeah, definitely 11.
12,
Definitely 11.
12.
12 again. All right.
Oh, 12's up there again? Oh my god.
So notice I currently have this counting how many there are. All right. And I'm going to now calculate the mean, x bar. So how do I do that in Excel? Does anyone remember the formula?
Average.
X equals
Average, right, is the quick way to do that. And I'm going to average.
3 to A103.
You got it, dude. So let's see. So I will
Drag.
double click and bam.
You see N.
I'm allowing it to have up to 100 values. So that way I could add a number here like 34, and then it'll update that. And why is the mean changing, guys? What did I do wrong? Look at this. What's wrong with that?
It says A105.
What's wrong? What's the Excel solution for that?
To make it to A16.
Oh, the money symbol.
I got a dollar that, right? And now when I drag it down, it is going to stay fixed as far as where it's pulling its reference from. Okay? So let's see. So I've got the mean. That's all I've figured out is x bar. So now the next thing I'm going to do is figure out what is xi minus x bar. So xi is just my data, okay? So how do I calculate that? What's that going to equal? No, I don't need dollars.
Oh, but you have to drag it out.
But I want this to change.
Yeah.
So I'm going to take my data point, xi, and subtract the mean. Enter. And when I drag this down, that's what I get. Okay? So 90 is 70.7 units away from the average. Okay? Right? 55 is 35 units away from the average. Okay? Now question, what do you think I would get if I averaged this list?
Yeah, you would get the same number. Yes, I agree.
So these are the distances that my data are from the mean, positive and negative. Now what about that trick I talked about where like, okay, where I had like 72 was 18 below, and this number is like, if it was 18 above, it would give me the average, right? Like where all of the points above and below have to kind of average out to be the same. So these are kind of my above and below values. So if I average those together, what does that mean?
That means error.
No?
Or it means that there's 50 zeros.
Yeah, that's computer speak for, we'll call that 0. Right? That's 14 zeros and then 152259. Okay? That's computer speak for 0. That's a rounding error essentially. But I just want to point out that the average of these differences is 0 because they should kind of balance each other out, like on a scale, like the average should be in the middle, some are above, some are below, but they should all kind of equal 0 if I was to add them together. And that's why I have to absolute value them. Let's see, I don't need that slash there. And it turns out there is an abs function there. So I'm going to have that absolute value, the function, right, cell to the left. And now I've just got the positive versions of these. Okay? So let's see. So what do I have to calculate? I've just found the absolute value of all of those things, all of those distances. And what am I doing to that list? Right? Sigma means add. So I want to find out what's the sum of this list. Equals sum of these guys. Right? Bam. So that is the total distance. All of our data points are from the mean. I was tempted to throw like just a paperclip at you to get you.
Alright, dude, it's alright. I was thinking.
Yeah.
You used to be aggressive.
So guys, how am I going to find the mean deviation? What do I do with that sum?
Divided by n.
Divided by n. I think I already calculated n here.
14.
It's 14. So I'm going to take this, divide by that.
That's the number of data points.
N is the number of data points. Yep. So that's my mean deviation. Okay? 16.47 means on average, my data is 16 units away from the middle. Okay? And watch what happens if I get rid of this 90.
No, it's going to go down.
Let's say if I change this 90 to a 9. So not only is my average going to lower, but the dispersity of my data is also going to lower because I don't have that crazy thing like making my data so dispersed. And so now my mean deviation is much smaller.
And then you get rid of the 55.
Yeah, let's make this like 10 or something, right? So the closer these numbers are to the middle, the smaller, wow, that's,
11. Yeah, 11.
wow, there you go. right, the less far away they are, right, this 28 is the next one that's far away, right, the smaller my mean deviation is. Where if my data is all clustered towards the middle, my mean deviation is small, right? If it's all dispersed,
Change the 4.
right, it's better. Change the 4. Is the 4 my new culprit of the furthest away? Yeah, and then the 15 is the next furthest, it looks like. So yeah, so I can get a smaller mean deviation as a result. But then once I throw one number in there, like 1,000, 10,000, it really screws up the dispersity of my data. So that would be why I'd consider that an outlier in that case, right?
Apply to the group.
Right? So that's the idea of mean deviation. It's the average distance my data is from the middle. So let's see. I'm going to email you guys kind of a prettier version of this because right now if I add a data point down here, it actually is broken because I'd have to shift all of these down to include that. So I don't know if you spotted that, but the mean deviation changed once I did that. Right, because it wasn't including that in the data. So I just want to point that out. I've got some if statements that will clean this up so it'll...
All you have to do is change it to 103.
Change what to 103?
Change the formula so then it's down all the way for each column, the formula. And it should, wouldn't it?
Oh, right. That's one thing I could do is if I just drag all of these down all the way to 103.
Double click.
Well, it wouldn't know to stop at 103 just yet. I could do that, but then I've got this issue where that shouldn't be the case. Because it's doing 0 minus 10.2 is negative 10.2, and it's skewing my data. So I'd have to throw in some if statements, and this is what I end up doing. I end up, watch this. Yeah, let's learn some little bit of Excel here. Watch this. Watch this. I'm going to say if this equals blank. Oh, what did I do? Nope. If that equals blank, there. Then give me blank. Otherwise, give me the average.
Commas mean then?
Well, commas separate different logical things. So notice that anytime the cell to the left of it is blank, it returns a blank. So now if I add 15, it'll give me a value there. Right? That one, it doesn't like the fact that I had a skip. Yeah, it's yelling at the ref. So I'm going to have some if statements on all of these columns that'll kind of fix things for us. That's weird. Well, either way, it's just a wide cell, that's all. So that's the idea of mean deviation, measures of variability. Tomorrow we're going to learn about standard deviation, which is similar to mean deviation. It essentially means the same thing. And we're also going to learn to find the standard deviation in a frequency distribution, right, when we don't know particular data values, but we'll be trying to estimate them. All right? So we are good, ladies.